Welcome to Space Journeys 109. Is there a microphone? Okay. Is not that? Higher? Higher? Okay. Perfect. Alright, let me pull my straight. Okay, yeah, welcome everyone to Space Journeys 109. We're, as you can see, in a new venue, and because of the weather, unfortunately, we're inside, but in the future, we will be outside, so don't worry about always being friends. I'm Noah. I'm one of the Space Journeys organizers. And for all the newcomers here, welcome. Space Journeys is Tucson's version of Astronomy on Tap, which is a network of events sharing astronomy in Mars and columns around the world. So how our show works is today we'll have one 25-minute talk, 20-minute intermission, and then an extended version of our astronomy news segment by Danny and Danny. There'll be two trivia questions in the first talk, and guess who answered? Gets merged from there's two questions in our setup because of the tight space. If you would like to live merge, you can come talk to the Space Journeys organizers, me and Amy, Sophie in the capsule. It's unfortunately time only, but donations are also greatly appreciated. To get us started, we have Sophie Lebowitz, who's going to tell us about how master black holes shape our universe.
So my name is Sophie Lebowitz. I'm a sixth-year PhD student at Steward Observatory. This is a really nice slide here, as you just saw. So I'm talking about how monster black holes shape our universe. So I hope you guys enjoyed that little video clip that we saw. What I was hoping you guys would notice from that video.
Sorry.
Is it for me?
That's me trying to fix the screen. Here we go. Also.
Okay, what I was hoping you guys would notice from that video is that there are a lot of different kinds of galaxies in our universe. So, galaxies.
Sorry. Trying to do this in between video. Alright, we're good. I shouldn't.
So, galaxies come in different shapes, sizes, and colors. So, what determines how a galaxy looks? A lot of it has to do with the contents of the galaxy. So, galaxies are made of gas, they're made of dust, and most importantly, they are made up of stars. Yeah. Okay, so some galaxies look bluer, they look a little bit more like spiral shapes. So these kinds of galaxies are made up of younger, bluer stars. We call them star-forming spirals because they are in a state of active star formation. On the other hand of the spectrum, we have galaxies that are made up of brighter, older stars. These tend to take on an elliptical shape, and we call these quiescent galaxies because they are quiet in the sense that they are not actively forming stars. Sometimes we also call these red and dead galaxies because they're dead since they're not forming stars. And in the middle, we have galaxies that have a mix of both young and old stars. These are green valley galaxies. And then, of course, there are galaxies that don't fall into one of these categories. But what I'm showing you here is not just a categorization of galaxy morphology. This is actually the evolutionary sequence for how galaxies change over cosmic time. So the fact that galaxies change over time is probably one of the most important discoveries that has been made in astronomy. And we're going to talk a lot about how this happens and why it happens. But first I want to talk about how you know that this happens. Okay, so let's talk about light travel time. So light, which is made up of photons, travels at a fixed speed of 186,000 miles per second. that is very fast. So right now you are able to see the light from the screen because the photons are leaving and then they're traveling to your eyes. And that light is traveling so fast, it's crossing such a small distance that you are seeing that light pretty much instantaneously. But once we start getting to larger distances, it starts taking longer for light to reach us. So I want to do a math example. This is the only one I have in my presentation. And I want to do it using our sun. So our sun is located 94 million miles away from the Earth. If we want to determine the time that it takes light from our sun to reach its Earth, we can just plug it into the simple distance over the speed of light equation, and we get that it would take 8 minutes and 20 seconds for light from the sun to reach the sphere on Earth. So what does this mean? Basically, this means whenever you look at the sun, you never see that light in that present moment. You are actually seeing the light that has been emitted 8 minutes and 20 seconds ago. So if the sun were to go out, you wouldn't know about it for 8 minutes and 20 seconds ago. So this effect starts to get more extreme when we leave our galaxy. Our nearest neighboring galaxy, the Andromeda, is located 2.5 million light years away from us. So this means that when we observe Andromeda, either with our own eyes or with a telescope, we never see Andromeda as it currently is. We see what it looks like 2.5 million years in the past. So if you have ever heard this phrase, that observational astronomy is a little bit like time traveling, this is where that comes from. So this has pretty big consequences for astronomers because basically what it means is just by looking at galaxies increasing distances away from us, we can actually get glimpses into earlier and earlier periods of the universe. And we can construct a timeline for how our universe evolved. So our universe is 13.7 billion years old. We are able to see as far back as the cosmic microwave background. We can't see all the way to the Big Bang because our universe is expanding at an accelerated rate. So I want to draw your attention to a very special period of this timeline right here. This is called cosmic new. This happened about 3 billion years after the Big Bang and lasted about 2 to 3 billion years. So if you think of noon as kind of being like the main part of the day, cosmic noon is kind of like the main time in the universe in which there's a lot of really extreme formation happening. So galaxies are growing faster than ever. They are making lots and lots of new stars. And galaxies are playing bumper cars with each other. They're colliding, they're merging, they're growing bigger, more and more massive. And we also find that the galaxy population in cosmic noon is dominated by a lot of these really massive star-forming spiral galaxies. So, as the universe evolves and we approach the present time, we find galaxies are growing. They are still getting more massive, but it's not happening as fast now as it did in the past. And the landscape of the galaxies that we see starts to change. We start finding a lot more of these quiescent, red and dead type of galaxies. So what does this mean? This means that from happening to now, something is killing a galaxy, shutting down a star formation. But what can do this? What can be so powerful that it is able to quench star formation in a galaxy? Probably you can tell by the title of the talk. It has something to do with monster black holes. More scientifically, we call these supermassive black holes. These are the kinds of black holes that live at the center of most, if not even all galaxies. So before we get into these, what they are, what they do, let's just do a little review of what a black hole is. So a black hole is basically a region in space where the gravity is so strong that nothing, not even light, can escape. A lot of people think that black holes are kind of like vacuum cleaners, that they suck stuff in. Black holes do not suck, either literally or figuratively. The best way to think of a black hole is to basically think of space as being like a very large, stretchy fabric. Objects that have mass will bend this fabric, forming what we call a gravity well, and when matter gets too close to that gravity well, it will get pulled in. So this happens with all massive objects, including Earth, the Sun. But in the case of a black hole, because they're so dense and their gravity is so strong, they form much, much deeper wells. So nothing, including light, can escape, which is why they appear black to us. So how does a black hole form? The simplest way for a black hole to form is for a massive star to reach the end of its life. Supernova, the core collapses, forming a black hole. So we call this a stellar mass black hole. They can have a mass ranging from 3 to about 100 of our suns. When we talk about things in terms of the mass of our sun, we call it a solar mass. So getting a little bit larger and a little bit more massive, we have intermediate mass black holes. These kind of black holes form when two smaller ones collide and merge together. And when this happens, this phenomena actually sends out a ripple in the fabric of space. We can actually detect that ripple here on Earth. We've done it with the LIGO experiment. And we can take that frequency of the ripple and convert it to sound waves. So I have here the real sound of colliding ripples. Whenever I show that to elementary students, they go, "Oh, you guys are silent." So this kind of black hole has a mass of about 100 to 100,000 suns. So supermassive black holes, as implied by the name, are more massive. Does anybody want to guess how massive the largest supermassive black holes can be in terms of our sun? This is our first out of two trivia questions.
D.
Yeah.
E.
E. Does anyone else want this?
C. D.
C. Okay. Who said D?
Me.
Okay. Answer is D. Yeah. We can't quite get to a trillion solar masses, but we can get up to a billion solar masses. So, a billion is a little bit difficult to wrap our heads around because it's a very large number. So I want to put this in terms of a scaling relation using optics on Earth. So let's just pretend for funsies that the sun has the mass of a small car. Stellar mass black hole compared to the sun, which is now, would have the mass of the sun. Getting more massive, an intermediate mass black hole, 100,000 times more massive than the sun, would be, compared to the small car, it would be an aircraft carrier. So if anybody wants to guess what kind of object I'm going to use, so a supermassive black hole, which can be up to 1 billion times the mass of our sun, would be all the buildings in New York City. Very, very massive. Okay, so how do they form? How do they get so massive? These are very special black holes compared to the other type. No, I'm not biased because I studied these. So these are the ones that form at the center of galaxies. A galaxy can have millions of supermassive black holes, can have several intermediate mass black holes, but it will generally only have one supermassive black hole. So I have here a very general 4-step recipe for creating a supermassive black hole in simple terms. Don't try this at home. So step 1, create a galaxy. Galaxies are made up of gas and dust. That gas and dust will clump together through gravity, forming the first galaxies. Step 2, you got a galaxy, gotta pick some stars. So stars are made of gas. However, that gas requires 3 main ingredients. Gas has to be cold, has to be dense, it has to be molecular. So within the galaxy, clouds of cold, dense gas collapse under the gravity. Their dense cores will get very hot, they will ignite, and they will start burning their fuel. I also want to mention step 2 and step 1 are kind of happening at the same time. So step 3, create a black hole. So this is just one theory of how supermassive black holes are formed, but massive stars are supernova, forming, this time people call it a seed black hole. The reason why we call this a seed black hole is the way that you can plant a seed that grows into a plant. A seed black hole is a black hole capable of going into larger, more massive black hole. So step 4, grow the black hole. This can happen in a couple different ways. It can collide and merge with other black holes. It can also grow by being fed in matter. So if matter gets pulled in by falling into the gravity well, it will feed the growth of the black hole. We call this process accretion. And this is a good word to remember because I'm going to be talking about accretion benefits. Also, if you have ever seen, I think they're called like a spiral wishing well that they use for charity donations. You might notice that when you drop a coin into that, it doesn't fall straight in, it will spiral around like that. So this is what happens during accretion. The matter gets pulled in a spiral formation. And it forms what we call an accretion disk. So this accretion disk has all this hot charged particles. They're colliding with each other. There's a lot of friction, a lot of gravitational forces. So you can probably imagine that stuff in the accretion disk is getting really hot, really, really bright, really high energy. At this point, the supermassive black hole has now become a very special kind of object that we call active galactic nucleus. So, nucleus just refers to center, galactic is the galaxy, and then active refers to the fact that the supermassive black hole is in this active state, it's actively eating and growing. So active galactic nuclei, for plural, is what I study. It's what I have been studying since I was an undergraduate. And since this is a little bit of a mouthful, for short, we call it an AGN, which is great, so I don't have to active galactic nucleus over and over again in my papers. Okay, let's go over what makes up an AGN. Here are the components. So at the very center is the obvious one. This is the supermassive black hole. So that radius of the black hole is determined by the event horizon. That's basically just the distance past which no light can escape. Getting further out, we have the accretion disk that we talked about. Getting a little bit further out, we have this donut-shaped structure composed of dust that we call the torus. Here I have another artist image of a torus. Basically, this forms as matter on the outskirts of the accretion disk, starts to accumulate, and at this radius, the temperature cools down just enough that the dust is not getting disintegrated. And then you may also notice that there is a stream of light. Where's my laser? Stream of light here. That it looks like it's coming out of a black hole, but it's not actually coming out of a black hole because nothing can come out of a black hole. This is called the jet. So the jet is produced by the rotation of hot matter in the accretion disk. This generates current, which produces magnetic fields. Fun fact, for those who are interested, the magnetic fields that we have here on Earth are actually produced by the rotation of hot magma in Earth's core. So, around an AGN, this phenomenon is a lot more powerful, to the point where those magnetic fields can essentially build up on top of each other, and they can actually fling out these high-speed particles into space. And that stream of high-speed particles is the jet. It also emits a radio frequency, so we call it radio jets. And I have here, this one is actually a real image. Most of the images I've shown are artist impressions, artist animations, but this is a real image of a radio jet in the galaxy's Hercules A. What I want to point out is that center orange dot at the very center. I don't know why I can't get mine. There it is, right here. That is the visible portion of the galaxy. So that's how powerful the radio jet is to be coming out that far. Very, very powerful. So all of these different components of an AGN are very energetic phenomena. They emit light across the electromagnetic spectrum, making active galactic nuclei some of the brightest, most high energy phenomena in our universe. So this is our second trivia question. Does anybody want to guess how bright an active galactic nucleus is compared to our sun?
D. C.
Okay, well, if you said D, E, F, or G, you're right. So AGN can take on a range of brightness, range of luminosities. Once we start getting to a trillion times brighter, we start hitting the regime of a quasar. So a quasar is basically the brightest active galactic nuclei. All quasars are AGN, but not all AGN are quasars. And I want to show you guys a very special little guy located, he's 12 billion light years away, so that's right on the cusp of cosmic moon. This is the brightest quasar ever found. He is 500 trillion times brighter than the sun, which is crazy. So what happens when the active galactic nucleus consumes too much matter? So you can probably think about what happens when we consume too much food. Its accretion disk gets really hot, really bright, it has too much energy, it can't hold on to all that energy, so it begins to release the energy into the galaxy. Energy that is released can actually have a very big impact on the galactic environment of the host galaxy, specifically on star formation. So if you guys remember back a few slides ago, in order to form around stars, we need gas that is cold, gas that is dense, and gas that is molecular. So anything that disrupts that will disrupt star formation. So here I have a little animation. I have a galaxy with some H2 clouds. That's the raw fuel for star formation. So when the AGN releases energy, it can do one of three things. It can heat the gas so it's not cold. It can ionize the gas. That just means it's ejecting an electron from the orbital so that it is not molecular. And it can also create winds that can actually blow out the gas in outflows, thereby removing it back into the host galaxy. So through these mechanisms, the AGN is able to shut down the formation of new stars in the galaxy. We call this process feedback. Feedback is what I study. So I took a few minutes to tell you guys a little bit about what it is that I actually do as a graduate student. So out of these three feedback mechanisms, I focus on this one. I focus on AGN ionization, specifically AGN ionization and cosmic neon. As a reminder, that's that really interesting period of time in which galaxy formation is at peak and forming a lot of new stars. So what exactly is being ionized by the AGN? The answer is oxygen. Oxygen is ionized. And it's not just being ionized once, it's actually being ionized twice, which we denote by this symbol O3 for doubly ionized oxygen. So this line emits at a characteristic wavelength of 5,007 angstroms, which puts it into the visible portion of the wavelength range. Does anybody want to guess what color this line appears to us? Yeah, go ahead.
Bluish?
Bluish? No. Oh, this one.
Green? It's bluish.
Doesn't it? Okay. Yeah, it's weird. Okay, so if you're wondering where all the green gas is, the answer is that it's not here, and it's not on Earth, it's not in our solar system. So this is a special line called forbidden transition. It requires very extreme environments for it to form. It requires the most low-density environments in the universe. So there's only two places you can find this line, either around a hot O-star or in the vicinity of an active galactic. So how is the oxygen getting ionized? Well, we have that very hot, bright accretion disk that I talked about quite a bit. It releases these ionizing photons, ionizing radiation into the environment, which travels through those oxygen clouds and ionizes them, again, not once, but twice. So if you guys also remember that diagram that I showed, surrounding the accretion disk, there is the torus, composed of dust. So this actually blocks the direction that the radiation can travel. So instead of it traveling outwards horizontally, it actually has to travel perpendicularly in these cones. And we call these cones ionization cones, which is more specifically what I study. So here I have an example of AGN ionization cones. This is a real image of a nearby galaxy. This is NGC 292. And I really like showing this example because it really shows how well defined and how big those cones are. Just for reference, the radius is about 5 kiloparsecs, which is 100 quadrillion miles. So if you were to run from here to Pluto 100 million times, that's that distance. So this galaxy is really close to us. I study galaxies at cosmic neon, which is 11 billion light years away from us. And cosmic neon galaxies look smaller, and they look fainter. And then there's a third problem, which is cosmological redshift. So basically that doubly ionized oxygen photon, we have seen invisible wavelengths, now has to traverse an expanding universe in order to reach us. And as it's traversing this expanding universe, its wavelength is getting stretched out. So by the time it reaches us, it's no longer in the visible portion of the spectrum, it's out in the infrared. So if we want to detect this line in cosmic neon galaxies, we need a very powerful infrared telescope. And a telescope has to be in space because our atmosphere blocks a lot of infrared light, which is probably good that we all don't get skin cancer. So, most of you probably know that in 2021, we launched a very powerful infrared space telescope called the James Webb Space Telescope. And this is what I use to study ionization cones out of cosmic neon. And here I have an example of ionization codes that I recently discovered in the cosmic neon galaxy. I drew some white lines on it to show you guys where the cones are. It's basically that green emission. If you're feeling a little disappointed by how this looks compared to the last one that I just showed, I would say please don't be, because this galaxy is 11 million light years away, so this is actually very cool that we can do this. So what does this tell me about an active galactic nucleus? So the extent of cones is correlated with the AGM luminosity, correlated with the energetic output of a neutron. Basically, it just means that larger cones equals the more power of a supermassive black hole. This will give you some hints as to whether or not there needs to be feedback happening in the galaxy. The reason why that's important is because AGM feedback is what can make a galaxy that looks like this lovely blue star-forming spiral transition into a red and dark elliptical galaxy like this one. Alright, so what does this mean for us? Because we live in a galaxy, and the fact that galaxies die might be the first time that you're hearing this, you might be wondering, what is the fate of our own Milky Way galaxy? So we are a spiral galaxy. We are currently in the Green Valley. That means that we are in that transition zone. But things are going to change in our future. We are on a collision course with our nearest neighboring galaxy, Andromeda. So we're going to hit them in about 5 billion years. And when that happens, the two supermassive black holes will merge. Stars will get flung around. There may be some new gas that can cause a little bit of star formation, a little burstiness of star formation. And a lot of that gas will get dumped onto that new, bigger supermassive black hole, feeding it and possibly even triggering a very luminous quasar phase. And then at some critical point, it'll have too much energy, and it will trigger feedback, which will rapidly quench star formation in our galaxy, causing the new Milk-Dromeda galaxy to die. If you have anxiety about this, you'll be dead way before it happens, so don't worry. But yeah, to end with, we live in a very diverse universe of changing, evolving galaxies, thanks in part to monster black holes. If you would like to know why I say in part, please feel free to ask me any questions. Thank you.
First of all, dumb question for conspiracy theories. See, black holes generally, are they generally the sun, galaxy, or star, or do they kind of just like complex like
I'm just gonna Google that one because that's way before the time that I studied. So that's a good question. I'm not too sure.
also for the time I studied, so that's fine.
I know what happens in like the first few 100 million years of the universe. I know it's a very controversial theory. There's another theory, and then even with the sea black hole theory, it's possible that it doesn't even happen. It may not even happen from a supernova. It could happen from just direct collapse of gas clouds.
What's the end?
Oh, thank you for asking. Okay, in part to monster black holes. Okay, so galaxies change. Supermassive black holes is not the only culprit of this. There are other culprits. Some of it has to do with interactions between galaxies, but some of it also has to do with stars. So I mentioned earlier that oxygen, the ionization of oxygen, can also be produced by hot O stars. So stars can also be responsible for changing the landscape of a galaxy. And really just one opportunity to show these really cool James Webb images. So the green emission in these galaxies is all doubly ionized oxygen. And I just wanted to highlight the fact that not all of them take on those cone-shaped morphologies. Some of them are spirals here, and some of them are these like point sources, and then some of them are not. So this just indicates that black holes, monster black holes, are not the only thing that can be ionizing oxygen in a galaxy. Stars can also play a role, and this is something that's important to look into.
Do we know what role, if any, dark matter plays in the formation of galaxies, or how it might be affected by these jets that affect ordinary matter?
I know that dark matter plays a really big role in the formation of galaxies, but I don't think I can comment on dark matter. Yeah, go ahead.
How do you weigh a black hole?
You can't weigh a black hole. We have physical equations that we can use to derive an estimate for the black hole mass.
I have a question. So daily, are you looking at new data from the Space Telescope, or is it like archive data now?
Yeah, that's a good question. Yeah, it's mostly archival. The objects that I'm showing here, what I've been working with is in the GEMS field. That's the JWST Extragalactic Medium Band Survey. That's what it stands for, and that is archival.
There is one that one on the bottom, the second from the left looks so different.
This one?
Yeah.
It's a really good question. I could definitely talk about that for 10 minutes. Okay. So I can't say for sure that I know why, but I can take a guess. So when I showed that image of the ionization cones, I mentioned how that has to do with the torus, the dusty torus. You can think of the torus as like a shade on a lamp. It blocks out the direction that the light can travel, so it travels in these cone shapes. But if you were to think that instead of viewing the active galactic nucleus from that, we call it an edge-on perspective, if you just flipped it and it's face on, then you're not seeing that extended light. It doesn't look like cones anymore. It might look more like a circle, like that. So this is actually a really big deal in my research because I have to figure out how the angle that I view these objects might affect what I'm able to learn about these objects.
All right, let's thank Sophie again. I'm gonna call my student again. This is the first time I've ever emceed any of this. So, okay, if you are a trivia winner, feel free to come find one of the organizers. We'll kind of glob in this corner over here right now. And to pick out your merch that you won. And we will be back in 20 minutes with what's called 8:20 to hear about astronomy in the news. And please fill your drinks, relax, and don't forget to take your martini. Steward postdocs, Danny and Jackie. Tell us about goings on in the nighttime sky, an extended version of astronomy news.
My beautiful news typey font is wrong. Okay, welcome back to Spacecraft's News Roundup. We know you desperately missed us and have felt completely in the cosmological dark without Danny and me to regale you with the goings on of the night sky. You might be wondering where we were when we took our brief hiatus. Were we off in space? Were we pondering? No. We were on our computers doing the exciting part of astrophysics, sitting around thinking about numbers. Next, please. Here's some stuff about numbers. Somebody asked about how to weigh a black hole. Here's how. Very good. Not for something completely the same. They found a black hole with the James Webb Space Telescope. This one's special, though. We've known about supermassive black holes forming in the first billion years of the universe's existence, if that includes you, not just me, since they'll never make me shut up about them, but astronomers remain puzzled at how fast they would have to grow to get so bright. Quasars are the really bright guys that you heard about. They're heating up so much gas around their supermassive black holes that they outshine all the stars in the galaxy. And they can grow to an astounding billion times the mass of the sun in only a few 100 million years. We thought maybe those guys are just the rare big dogs. A statistical fluctuation of the universe. But to really understand black hole formation, we must look for the common man, the proletariat, the somewhat massive but still supermassive black hole. And in comes the concept of the little red dot. Here it is. She's little, she's red, she's a dot. JWST images found tons of small red things at infrared wavelengths, but whether these guys are small as black holes or red galaxies requires a spectrum. And that's what you see here, spectrum, where we break up all the light into its components, like a prism. So LRV spectra over the last couple of years have lent credence to their maybe being predominantly black holes, but we thought the majority of them lived around redshift 4 to 6, cosmic noon. Maybe cosmic 11 is. But in a new paper by Cosmic Frontier Center postdoc Anthony Taylor in Austin, Texas, they report a new spectrum of a little red dot at redshift 9, which is about 500 million years after the Big Bang. That's crazy. Okay, here I am. It's not Bubby's Bagels, but if it was, I would say hold the capers on my bagel box, please. And that's because this data comes from the CAPERS program, the usual tortured acronym. The CANDLES Prism Epoch of Reionization Survey. CANDLES also stands for sun. It's headquartered at NORLab in Tucson, and it takes spectra of young galaxies at high redshift to boost T. So Taylor's version here shows a gorgeous spectrum, as well as the results of fitting various models to the energy output, like a young galaxy or a black hole. And so in the red, you see where we assume this is coming from the AGN. Somebody asked, how do you weigh a black hole? Right there. Wrong. That's a 3. Where is the hydrogen line? Here it is. It's really big, it's really broad. It's moving very fast. The object shows a smoking gun signature of an accreting black hole, and it's broadened H-beta profile, which basically means a large cloud of hydrogen is orbiting the black hole, and as it eats, it throws off a characteristic bright velocity profile. That's how you weigh a black hole. And stars simply could not reproduce this broad H-beta profile. It keeps us up at night when we weigh a black hole. So we use the velocity profile of H-beta. We figure out how massive the pretty massive supermassive black hole is. It tops out around 200 million solar masses. Not record-breakingly massive like a quasar, but it's still simply too big for us to understand black hole formation. So the paper goes on to discuss a number of formation pathways to black hole's growth and luminosity, including concepts like direct collapse black holes, runaway stellar collisions, and primordial black hole formation. Further tests of supermassive black hole formation await more JWST data. We always need more and more data. But for now, we can be excited to see a spectrum of a little red dot from when the universe was only 3% of its current age. And I thought, if the whole universe was a year, what would be 3%? 3% is January 11th. So this is the January 11th of time, if you will. Thank you.
I mean, I feel like very related things is also the gender, like at this time, right?
So true.
Just a thought, you know. Okay, so I started my news story tonight, maybe a bit of deja vu, because I started this space draft, as I've started many space drafts since I've started co-hosting here, talking about the astronomer's quest for exoplanet wiggles with JWST. And by wiggles, I mean looking for exoplanet atmospheres, and by the request for them, I mean just hoping and hoping and hoping that you'll find something that isn't just one more goddamn flat line. So there's a lot of flat lines, so what here kind of warrants a new news story, and so this is because of the target. So new observations have come in from JWST of the TRAPPIST-1 system, which if you've heard of exoplanets, pretty likely you've heard of this system. So what makes it so special? So TRAPPIST-1, an artist rendition is right there, is an ultra cool red dwarf that hosts 7 transiting small exoplanets. So it's, I don't believe it has the most known exoplanets, but it's very high up there. And so this makes it a very interesting lab for understanding exoplanets, because in just one system, you can kind of compare how all the planets are to each other and say something about their differences in a control environment. And also, since the star is so cool, that means that the planets are relatively quote-unquote large with respect to it, so any signals of the planets would be pretty large. And of the 7, a few of them actually reside in the habitable zone. Of course, that does not mean that they're habitable, but there could be liquid water on their surface. So understanding these planets is a really important probe of how planets around these very, very common cool dwarfs might be. And so because of all of these unique characteristics, TRAPPIST has been the target of many observational campaigns, including many with JWST. And what they do is they do transmission spectroscopy, so these planets transit, they pass in front of their host star. That means when they do so, the starlight passes through an atmosphere that's there, and then we can pick up those signatures and determine is there an atmosphere or not. So they've already put out a bunch of studies on some of the other planets. So planet B, the one closest in, and C, the next closest in. They don't have atmospheres, we're pretty sure, which is not surprising since they're so close to the star. And then just last month, there was a study on the D planet, and that also probably doesn't have an atmosphere, but just this month, they put out a study on planet E, which is actually the one that might reside most in the habitable zone. And so they don't see any huge signatures of an atmosphere, which is not necessarily a bad thing. So there's no thick, like, hydrogen envelope, which probably wouldn't be good for life. They also don't see any clear CO2 signatures, so that means it's not like Mars, like a CO2 snowball planet, or like Venus with all such a greenhouse effect. But if you look in this spectrum here, there are a little bit of wiggles. That could be due to a nitrogen-rich atmosphere like our own, so that's really exciting. Now, of course, it's also a flat line because it appears to be a flat line. So it could be a flat line, but this is a little promising for a potential atmosphere around this potentially habitable planet. And of course, like Jackie said, more data. We always want more data, and there is more data of this planet coming. And what's really cool is that they're going to be getting something like 15 or 20 more transits of this planet. But what they're going to do is they're going to observe transits, basically of 2 of the planets right after each other. That one that's closest in without an atmosphere, and then this one that might have an atmosphere. And so by comparing those data, you can actually figure out if what you're seeing here is due to the planet or not, and not just due to the starlight being a mess. So I think that's a really cool way to do it. And so yeah, flat lines are still kind of the bane of existence, but there's a lot of data coming, so expect to hear about flat lines from me every space draft news from here to the end of the universe.
All done. But you thought it was done. You're silly. Okay, Euclid Avenue, no. Euclid Avenue in Tucson, Arizona, the greatest place in the world for astronomy and space exploration, but sometimes we unfortunately gotta handle it to the Europeans with their Aperol spritzes and their no air conditioning. Having asses Here we are with Euclid. In 2023, the European Space Agency launched the Euclid Space Mission, an optical and infrared telescope that has the ambitious goal of mapping out nearly 1/3 of the entire night sky by 2030, or 14,000 square degrees. Silly, I can do that with my eyeballs. This might be old news if you're a Euclid freak. I doubt it though. So this past March, sorry, I was busy. The ESA released its first mosaics with images taken in the Fornax and the Draco constellations. These mosaics total 63 square degrees, or about 300 full moons. I know that sounds like a tiny pinpoint in the grand scheme of the universe. That's because it is. But these deep fields contain a rich spoonful of exotic galaxies and black holes. Here they are. So this gorgeous gallery of galaxies contains 380,000 objects. The galaxies are observed in all kinds of shapes, spirals, cigars, ellipticals, sizes, colors, and rings. There are hundreds of examples of Einstein rings, not cool and funky jewelry, but instead of humdrum some little effect of relativity, light from background galaxies can be bent like a lens by a massive galaxy in front of it, a concept called gravitational lensing. In a perfect alignment, we would get a beautifully perfect circle. They go on and on about this in the press release. Do you see one here? No! So it's not in the press release, but just imagine a circle around the galaxy, and that's a ring. And you might be wondering how we could possibly classify 380,000 galaxies by their shape, sizes, and colors. Euclid is pioneering a combination of AI algorithms, the way of the future, and citizen science projects. That's you. Like Galaxy Zoo, which you can join if you like to look at beautiful galaxies. Here you go, QR code. So we can build an unprecedented catalog of massive objects. A quick couple centuries after the navel-gazing Messier and Hubble catalogs of cool broads in the sky, we are now in big dog territory. Millions of galaxies, all the way back to cosmic dawn. Euclid will map and observe the largest scale structures in the universe to learn more about gravity and dark matter and dark energy. You know, a quick Saturday to-do list. Learn more about dark energy. Anyway, so you should check out zooniverse.org. Here you go, QR code, and you can use your special eyeballs to classify galaxies like this. So instead of watching TikToks when you're, on the toilet on cutting time, you can classify galaxies. So anyway, Euclid's got a lot more in store. Stay tuned for more pretty infrared images. Okay, I'll be back in a few minutes. Thanks.
So I guess we're going to keep the ball rolling with some exciting new telescopes coming online. As I show off some of the first look images from the Vera Rubin Observatory, which just came out a couple of months ago. And so what? Oh, okay, yeah, we got some fans in the audience. That's great. Don't fact check me if I did anything wrong. So what is Rubin? So that's Rubin right there. So it is a telescope in Chile that is going to do something quite remarkable and really revolutionary for the field. It's going to take extremely high quality images of the entire southern sky every few nights. And it's going to do that for about a decade. And so this is just a remarkable feat in terms of, well, the science that's going to come out, but also just the technology that has gone into it. The telescope, the camera, detector, all the instrumentation really have to be specially designed to provide the sensitivity and a really wide field of view necessary to actually get those observations so quickly. And this observatory, so just to say, it's named after Vera Rubin, who was an astronomer who was really crucial in kind of our steps towards understanding or detection of dark matter through her work on galaxy rotations and the weirdnesses that come with that. And so with this all-sky survey, the LSST, the Legacy Survey of Space and Time, that used to be the name of the telescope, but we're moving on. So this survey will work toward a lot of science goals, and that includes studying dark energy, dark matter, finding transient events, so it's going to be able to detect things in the sky that weren't there the last time it looked a few nights before. So things like supernova, gamma ray bursts. It'll tell us about how stars are varying, galaxies are varying, it'll map the Milky Way, all of the stars, and it'll also search for tons and tons of small objects in our solar system. And so all of this, taking all those images every night, is going to require some pretty wild data processing capabilities. And also because they have to do things like follow supernova, they have to process these all really, really quickly. And so there's a very complex system in place about getting the data off of the telescope and then to processing centers, and there's things with like secrets because you could observe, I guess, like like undercover things from the government. I don't know. This is weird stuff. But so they'll be reducing these terabytes and terabytes of data every day. And we won't have to wait too much longer. So Rubin is undergoing commissioning now. It's taken its first images of the sky. It has some reviews coming up, and then hopefully this survey will start in the next few months, by early next year. And so just some of the images that they released really give us a glimpse at the science that's going to be done. So here is a star-forming nebula, the Trifid and Lagoon Nebula, which are regions of intense star formation. So Rubin will map these regions really well, very deeply, and will understand how this gas and dust turns into stars, how those stars evolve over time. Here is a look at the Virgo cluster, which is the nearest large galaxy cluster to us. And so with these images, so here is like millions of galaxies. It's like a fraction of a percent of all the galaxies that Rubin will observe over time. And so someone's able to see how galaxies kind of interact with each other. And then also we will detect thousands, actually millions and millions of near-Earth objects, asteroids, comets, things like that. Here is just like a glimpse. All of these dots are like new asteroids that Rubin found in like a night or something. It found like thousands. It's gonna be pretty crazy. And so they'll make sure that we don't get hit by anything and then all die, because I guess that would be bad. So Rubin really is going to expand our capabilities pretty crazily, and so like you're stuck with me talking about flat lines, you'll be stuck with me talking about this observatory for quite a while also. Thanks, Brett.
So before I start this last written story, am I severely aging myself if I beg of you to recall the hit 1999 movie Xenon Girl of the 21st Century? Woo! Thank you! Okay, am I crying into the void if I ask if you remember Protozoa and Microbes' hit in movie single? Zoom, 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 make my heart go boom, boom, my supernova girl. Thank you. Anyway, Supernova Girl is here. She's not here, but she's in the vicinity, and she is University of Arizona grad student Krista DeCourcy. And in the spirit of our famed gem show in Tucson, Arizona, Steward Observatory birthed JADES, the JWST Advanced Deep Extragalactic Survey. JWST also stands for something. Okay, well, one of JADES' core goals was to identify very high redshift galaxies with infrared imaging, but wait, there's more. Because the light from high redshift galaxies has been traveling towards us for billions of years, we can pretty much guarantee that nothing is going to change particularly quickly. That is, unless there is an unknown event causing rapid fluctuations in brightness. So most of the universe, at least on human timescales, is as David Byrne of Talking Heads put it so simply and so poignantly, same as it ever was. But supernovae, the spectacular explosion of a dying massive star, burst forth with a blinding light, and it steadily fades over timescales of days, months, and years. The trick is, though, to catch it in motion, which requires looking at the same spot a bunch of times, like, watching a horror movie by yourself and taking a shower. But the JADES Transient Survey is basically doing that by imaging patches of the sky taken a year apart. And because of wibbly wobbly timey-wimey stuff, that year is only a few days in the distant corners of the high redshift universe. And so in Chris's latest paper, she reports the discovery of a transient event at redshift 5.2 when the universe was about 1 billion years old. And it's hosted by a bright galaxy, which you can see here. So this is the same galaxy in different colors. And this is the first time we looked. And there it is, combined in the different colors. Then we looked again, and here it looks a little bit different. And then we subtracted one from the other, and look, there's light left. If you took the picture of something twice, and you subtracted one from another, you should see nothing left. Unless there's a ghost, and the ghost is the supernova, and there she is. And so by subtracting the older image from the newer one, we see clear residual light in one location, corresponding to some type of brief fading event. There are a bunch of things that can happen quickly in the universe, because I actually lied to you. But the paper talks about other kinds of transients that it rules out, like a black hole that is fading and brightening because of its eating and shopping and this and that, or a black hole Pac-Man, which is a tidal destruction event when galaxies and black holes are. You know what? I'm not going to explain it to you because truthfully, I can't. But they conclude that it is most likely a core collapse supernova, which is when a supernova collapses in its core, which is also a star that is at least 8 times more massive than the sun. That's all I can tell you. But this tantalizing discovery awaits what? More data and a spectrum of its hydrogen and helium features. Which is apparently how you get all the numbers and letters after supernova. I learned yesterday that a type 2N supernova is for narrow. So you can get a PhD and learn new things every single day, but just by listening to your friends talk at you and you realize you don't speak the same language. Long story short, TLDR, a supernova went off in this galaxy. Big, bright, beautiful, amazing, at super high redshift. We usually only see these things very close to us. So this is really, really incredible work. Thank you so much for listening to me and Xenon, Girl of the 21st Century. Come back next month and I'll listen to Danny one more time. Thank you.
You can't like sign before we're done. Wow, all this leading is fine, no one cares. I don't have a song to sing, so nor do you want to hear that. Yeah, so I would say kind of that, as an astronomer, someone who's interested in space, I can say that we've long dreamed of visitors from beyond the stars, right? We think of aliens, spaceships, probes that bang whale noises at us. But astronomers have found a few of these interstellar visitors, but they aren't necessarily what you might think of to get hyped about, although some astronomers that I won't name might think so, but I'll get to that in a little bit. So what I'm talking about, I'm talking about interstellar comets. So these are comets that are passing through our solar system, but are not from our solar system, they're from somewhere else. We don't know where, but we know that they're not from here. The first one, Oumuamua, was discovered in 2017. I don't like how long ago that was. The second one, Borisov, was discovered in 2019, and just a couple of months ago, they discovered the third, 3I Atlas, and that's this little thing that's going across the street here, and that's there. So what is this thing's deal? So it was discovered by a telescope in Chile that gave it its name, Atlas, as it's kind of been approaching the inner solar system. And so, right, it was detected by looking and seeing it. This thing moving across the field of background stars, and then, telescopes, both professional and amateur, trained their eyes on this object, and were able to figure out its orbit and determine that it's actually coming in from outside of our solar system. So why are these interesting? Okay, we have plenty of comets, like, it's so faint, like, why do we care? Well, so our own comets in our solar system are often thought of kind of as fossil records of what our solar system was like at the beginning. So it is material that was used, well, not used because it's in the comet, but things like it were used to build our planets. And so it's really kind of an important probe of understanding how a planet like Earth and its habitability came to be over time. And so if we can study comets from other star systems, well, then that might tell us if they're similar, then maybe other planetary systems could have formed in a similar way and also have Earth-like planets. So there's been really intense follow-up, given that it's only the third of its kind that we've discovered. So at first they weren't sure if it was a comet or an asteroid, and kind of an array of data from the ground, from space, from Hubble, from JWST, have confirmed that it's a comet. They've detected gases, so this is a JWST image showing that it has CO2, it has water ice, it has other organic materials that are not uncommon in comets. Some of it looks a little different in abundance than what we're used to, some of it's normal, so there's some interesting differential kind of analysis to do. I don't really know about molecules, but I'm sure it's interesting. So this has not yet reached its closest approach to the Earth, which is going to happen right at the end of the year, and that is going to be after it closely approaches Mars, the Sun, and Venus. You can actually, if you just search like NASA 3i Atlas, you can actually see its journey through the solar system, which is pretty cute. And actually, because it's passing by some of these planets, it's actually going to be observable with, say, like orbiters of Mars. And so we're going to get a lot of data on this thing as it comes through. So now to go back to my reference to a certain illustrious astronomer who shall not be named, this has not been without controversy. There is someone who likes to say everything is aliens, and this is also apparently maybe alien. Now, I don't want to say, like, it could be, right? As scientists, we can't say that, we can't just scoff and say go away. But extraordinary claims require extraordinary evidence, and he was like, the orbit's weird, the orbit's not that weird. It doesn't have a coma, well, it has gases. So I would just say kind of interesting hypotheses sometimes become trolling after a while. Regardless, it doesn't have to be a spacecraft to be cool. I mean, would it be cool if it was a spacecraft? Maybe, or we'd all be dead. But this is still interesting. So even though some of us might be disappointed, we have to wait for first contact longer. We're going to learn a lot about how planetary systems form, and Ruben, to go back to my last story, is going to discover even more of these. And so we're going to start having a rich tapestry in the sky of potential alien spacecraft to talk about for years to come. Thank you.
Sarah, have any questions for Daniel and Matt?
Oh, boy.
All right, we'll call that a no. So our next space rest will be October 15th, hopefully outside, pending any unexpected weather, like monsoon season lasting a lot longer than it should. And I think that's it. So thank you all for coming, and hopefully we'll see you next month.